4A, primes, composites, and factors. So let's talk about a factor. A factor of a natural number is any natural number that divides the number evenly with no remainder. Okay, so basically you take a number that's not a decimal, and remember our natural numbers are our counting numbers, 1, 2, 3, 4, 5, 6, right? A factor is any number that you can divide into it that doesn't give it a remainder. 24, 6 is a factor. 24 divided by 6 gives you 4 with no remainder. 10, 5 is a factor. 10 divided by 5 is 2. So that's all we're saying with a fact when we're finding factors is if we take that number and divide it by another natural number, do we have a remainder or not? If there's no remainder, it's a factor. So I'm going to put a random number up on the board, well, a somewhat random number, we'll say. So let's say I have 8, 2, 5, 7, 6. Oops. Let's make that actually be a 6, right? 5, 7, 6. 1, 8, 4. 3, 1, 0. So that's what? That's the ones, the thousands, the millions, the billions. So that's 82,756,184,310. And I want to start determining whether certain numbers are factors of this. And if you're like me, you look at this and go, are you nuts, Mr. Davis? Seriously? We're talking about a number in the billions, and you want me to determine if certain numbers are factors of it? Well, what we're going to do is we're going to look at some little tricks, shall I say, for determining if certain numbers are factors of other numbers. And we're going to deal with the numbers 1 through 10. So how do I know if the number 1 is a factor of any given number? And the answer is, if it's a natural number, 1 is a factor. So you give me a natural number, 1 is always a factor, because you take any number and divide it by 1, you get that number back. So we're going to say that this is divisible by 1. Okay, so in blue I'm putting the ones that we determine are factors. It's divisible by 1, therefore 1 is a factor of that. Well, how do we know if 2 is a factor? We know 2 is a factor if we have an even number. So it's divisible by 2 if we have, and when we say divisible, that means you can divide it by that number and have no result. So basically it's saying it's no remainder. Therefore, it's basically a factor. But to know if a number is divisible by 2, it must be an even number, which means that it ends in 0, 2, 4, 6, or 8. And we look at this number and go, it ends in 0, therefore it is divisible by 2. What about 3? Well, 3 is kind of a trick to it. If you take all of the digits in the number and add them up, and that result is divisible by 3, then the original number is divisible by 3. Well, what that means is you could actually take all these numbers, add them up, and then you get to that point and you could take the numbers of the result and add them up, and you can keep doing so until you can tell whether it's divisible by 3 or not. So let's try that. 8 plus 2 is 10, plus 7 is 17, plus 5 is 22, plus 6 is 28, plus 1 is 29, plus 8 is 37, plus 4 is 41, plus 3 is 44, plus 1 is 45, plus 0 is 45. So we added them up and got 45. Well, I can look at that, and I happen to know that 45 is divisible by 3, but if I'm not sure of that, I could say 4 plus 5 is 9. 9 is definitely divisible by 3. So 82,756,184,310 is divisible by 3, because when I added them up, the digits up, I got a number that's divisible by 3. And if I wasn't sure with that, when I added those digits up, I got a number that was divisible by 3. So it doesn't matter. You could have a 20-digit number up here. You add them all up, and just keep adding the digits together until you get down to the point. You're going to reach a point where you get to a single-digit number, and it should be obvious whether that number is divisible by 3. So this number is divisible by 3. Awesome. I'm going to leave that 45 up there because it might become handy to us in a little bit. Okay, so divisible by 3, you add them up, so the sum of the digits, I'm going to say. Remember, sum is just a way of saying addition, the result of addition. Sum up digits, and then if that's divisible by 3. So if you sum up the digits and that's divisible by 3, then the number itself is divisible by 3. What about 4? Well, 4's got a little trick too. For 4, you look at the last 2 digits. And if the last 2 digits are a number that's divisible by 4, then the number is divisible by 4. So in this case, the last 2 digits are 1, 0, so the number 10. 10 is not divisible by 4, so this number is not divisible by 4. Now, why does that work? Because 4 times 25 is 100. So as soon as you get up to the hundreds place or beyond, all of those are divisible by 4. It's just these last 2 digits, that part there, which we have to determine whether it's divisible by 4. What about divisible by 5? Well, divisible by 5 is very simple. If it ends in 0 or 5, then it's divisible by 5. This ends in 0, so it is divisible by 5. Divisible by 6. This is actually going to be one of our easiest ones, because we've already done the rest of this work. If a number is divisible by 2 and divisible by 3, then that number is divisible by 6. So all we have to do is say, was it divisible by both 2 and 3? It was divisible by both 2 and 3, therefore it's divisible by 6. Oops. Trying to keep to my color scheme here. So it's divisible by 6. Divisible by 7. Okay, now here's where there is a method that you can use to determine if a number is divisible by 7, but it is so much work to do that method, to remember that method and do that method, that you might as well go for this really fancy method of use calculator. Use a calculator. Divide by 7 and see what happens. If you get a whole number as the result, then it's divisible by 7. So I've got 8, 2, 7, 5, 6, 1, 8, 4, 3, 1, 0. And I'm going to divide that by 7. And I got 1.182231204 times 10 to the 10. Okay? Which means that didn't tell me a lot. So we might be in trouble here. My guess would be that it's not. I'm going to do what I tell you never to do, and I'm going to pull out a calculator. Actually, I don't even know if I have a calculator other than that same one on here. I should. Does it have a built-in calculator? In my files? just got my Droid 48 on here. I do not have another calculator, so we're going to have to just go with it. I don't know. We're going to leave 7 as a question mark. This is a big enough number that I would have to either do the division by hand or switch to a calculator that gives me more digits. Sorry about that. What about 8? Okay, now don't give me the answer that if it's divisible by 2 and 4, it's divisible by 8, because that's wrong. But if it's not divisible by 2, or it's not divisible by 4, then it obviously can't be divisible by 8. But 8 follows a similar method to what 4 did. If the last 3 digits create a number that's divisible by 8, then the number itself is divisible by 8. And that's because 8 times 125 is 1,000. So once we get to thousands place and over, that's all divisible by 8. But 100 is not divisible by 8, so we've got to see what happens here. So 310, is that divisible by 8? Well, I happen to know that 320 is divisible by 8. So 312 would be divisible by 8. 310 is not divisible by 8. So 8 is not a factor of this. 9. 9 works the same way as 3. Sum up digits. And if that result is divisible by 9, then so is the number. So we summed up the digits earlier, and that's why I kept that up there. It summed up to 45. And as I said, we can do the same thing of 4 plus 5 is 9. Is 9 divisible by 9? Well, obviously it is, because 9 divided by 9 is going to give you 1, right? So it is divisible by 9. And then our last one is it divisible by 10? If it ends in a 0, it's divisible by 10. So if it ends in a 0, it's divisible by 10. This ends in a 0, it's divisible by 10. So that's how we can determine whether the numbers 1 through 10, excluding 7, divided evenly to a natural number. So that's kind of cool. So that would allow us to find factors. Now I took a huge number. We generally wouldn't work with something that big. So what I want to do is I want to go for a smaller number, and I want to find all the factors. So let's say we take the number 28. And I want to find all the factors of 28. So what we're going to do is we're just going to work our way through and see if it's divisible by 1, if it's divisible by 2, if it's divisible by 3. So there was a reason for doing this, for doing all those things. So 28, we know if it is a natural number, it's divisible by 1. So 1 is a factor. Now, what I'm going to do that may be different than what some other people do is, if 28 is divisible by 1, what's the result? 28 divided by 1 gives us 28. So I know 28 is going to be a factor. So what I'm doing is I'm going to get pairs of factors each time, because 28 divided by this gives me that. So 28 divided by that gives me this. So I can get two at the same time. So I'm going to start from the bottom and also be starting from the top, which is going to allow me to get through my factors easier and eliminate risk of making mistakes or missing ones. So then I go, is 28 divisible by 2? Well, it's an even number, so it's divisible by 2. 28 divided by 2 is 14. Is 28 divisible by 3? 2 plus 8 is 10. 10 is not divisible by 3, therefore it's not divisible by 3. Is it divisible by 4? Yes, it is. 4 times 7. So 4 and 7. Is it divisible by 5? It doesn't end in a 5 or a 0, so it's not divisible by 5. Is it divisible by 6? Well, it wasn't divisible by 3, so remember, for it to be divisible by 6, it would have to be divisible by both 2 and 3. So it's not divisible by 6, and then you see we're already up to 7, which we already did. So if we want to put these in numerical order, and I don't require you to put them in numerical order, we could say it's divisible by 1, 2, 4, 7, 14, and 28. So that is the list of all factors of the number 28. So that's all the factors. We can list all the factors. Now, if you have more than one number, sometimes you want to find common factors. Common factors are those that occur in both of those numbers. So let's say we take 36 and 24. Put that pen away for a moment. 36 and 24. And I want to find all of the common factors. So what I'm going to do is I'm going to factor 36, I'm going to factor 24. Find all the factors for them. So obviously 36 is divisible by 1, leaving us 36. It's divisible by 2, giving us 18. It's divisible by 3, giving us 12. It's divisible by 4, giving us 9. It's not divisible by 5, it is divisible by 6, giving us 6. So, that having taken up that much space, I'm going to move the 24 below, and let's find all the factors of 24. It's divisible by 1, giving us 24. It's divisible by 2, giving us 12. It's divisible by 3, giving us 8. It's divisible by 4, giving us 6. And it's not divisible by 5. So now that I have those, I want to find the common factors. So they're both divisible by 1. They're both divisible by 2. They're both divisible by 3. They're both divisible by 4. They're both divisible by 6. They're both divisible by 12. And that's it. So the common factors are 1, 2, 3, 4, 6, and 12. 1, 2, 3, 4, 6, and 12. So if we're looking for the common factors, we find all the factors of both numbers, and then we look for which ones occur in both of them. So those are common factors. Now, in addition to common factors, so I'm going to write this down as common factors. There's also the greatest common factor. The greatest common factor, sometimes referred to as GCF, the greatest common factor. The greatest common factor is the largest number that is the factor of both of your original values. So if we look at this, we say, aha, the common factors are 1, 2, 3, 4, 6, and 12. So the greatest common factor is the largest of those. So in this case, 12 is the greatest common factor. So we factor both the numbers, find all the factors of each of them, we find the common factors, and then if we want the greatest common factor, it's just the largest number that's a factor of both of them. So that's pretty cool. Now I want to give you a little bit of a definition. I'm actually going to give you two definitions, and they're actually written right up at the top of the board here. Primes and composites. So, prime and composite. A prime number is a number that is divisible by exactly two numbers, one and itself. So a prime number is one that is divisible by exactly two numbers. 1 and itself. So a prime number is any number that's divisible by exactly two numbers, 1 and itself. Now a composite number, that's actually an easier definition. Not a prime. Any natural number that's not a prime is a composite number, meaning that it's divisible by more than two values. And I really shouldn't say any because there's also the oddball number, 1. It's not a prime number, it's not a composite, it's just itself, divisible only by itself. Right? So the number 1 is divisible only by itself. Remember, prime numbers divisible by exactly two numbers, one of which is 1 and itself. 1 is divisible only by 1, which is itself, so that's only one number it's divisible by. So that's why it's important to realize that. So what are your prime numbers then? Well, 1's not a prime number, it's its only thing there, right? It's by itself, so 1's not prime. So 2. 2 is divisible by 1 and 2. 2's prime. 3. 3 is divisible by 1 and 3. 3's prime. 4. 4 is divisible by 1, 2, and 4. Oh, it's divisible by more than two numbers, right? So the only even prime number is the number 2. Because any other even number is going to be divisible by 1 itself and 2. Who knows how many other numbers, but it's already guaranteed any even number is divisible by 2. Any even number is divisible by 1. Any even number is divisible by itself. So 4, 6, 8, 10, 12, etc. All even numbers other than 2 are composite numbers. So they're not a prime. 5. 5 is only divisible by 1 and 5. 6 is an even number, so it's not a prime number. 7. 8, no. 9, no. 10, no. 11. 12, no. 13. 14, no. 15, no. 16, no. 17. 18, no. 19. 20, no. 21, no. 22, no. 23, no. 24, 25, 26, 27, 28, 29, 29, 30, 31, 32, 33, 34, 35, that's right. So there are an infinite number of prime numbers, so nobody expects you to memorize all the prime numbers. But there are ones that you should recognize, 2, 3, 5, 7, 11, 13. Those you should recognize. You go, well, I can't divide that by anything. Okay, exactly. That's a prime number. I will tell you that there is no order or logic, I hate to say that, but there's no order or logic to prime numbers. There is no formula that you can use to find all the prime numbers. In fact, what they do to find prime numbers is they use a brute force method. They go to the next number, and obviously they skip any even numbers because even numbers are not going to be prime. So they go to the next odd number that does not end in a 5, because numbers ending in a 5 are going to be divisible by 5. So basically all they do is they go to the next number that ends in a 1, a 3, a 7, or a 9. And then they take it and they start dividing the prime numbers into it. And if they can get halfway to that number without finding a factor of it, then they know that it is a new prime, is another prime number. And why do we say if they can get halfway to it? Because once you get halfway, you're divisible by you're going on the opposite side of being divisible by 2. You go beyond that, you can't divide anything into it evenly. So there are still unfound prime numbers. You could actually become world famous for finding yet another prime number, because they're out there and nobody knows all of them. They're using computers and using brute force method to find them, and they're still, every time a computer gets more powerful and more capable, they're able to go a little further and find another prime number. So why do we care about prime numbers? Well, prime numbers can be really handy to us because they can be used to find a couple things that we like to find, such as greatest common factors and least common multiples. We haven't talked about least common multiples, but we will. So there's a couple things in mathematics that being able to deal with primes helps us to get to them. So our final thing I want to discuss at this point is prime factorization. So prime factorization basically says take a number and find all the prime numbers that multiplied together will give you that number. So you're finding all the prime factors. You're breaking down each of the factors into its prime equivalents. So that's what prime factorization is. So let's take a number like 24. So if we're going to do the prime factorization of a number, we just start dividing prime numbers into it, or dividing it up any way we see we can. If we see this is divisible by a number, divide by it, and keep going until all you have are prime numbers. So I see 24 and I go, well, that's divisible by 2, leaving us with 12. And I do have a tendency to start with 2's and pull out 2's until I can't do that anymore. And then I'll go to 3's and pull that out. And then I'll go to 5's and pull that out. Okay, so I have a tendency to work that way. But you may see other things. So I've got 24, I pull out a 2, I divide by 2, and I'm ended with 12. 12's not prime, so I take that and I say, well, I can divide that by 2, leaving me with 6. 6 isn't prime, so I say, well, I can divide 2 out of that, leaving me with 3. 3 is prime, so I've got 2, 2, 2, and 3, all prime numbers. This is called a tree diagram, where we're just taking a number and we're splitting it out, splitting it out, splitting it out. And what we're doing is we keep doing this until we get all prime numbers. Then we can say, well, that's 2 times 2 times 2 times 3, right? We divided out 2, we divided out 2, we divided out 2, we were left with 3. So 2 times 2 times 2 times 3, 2 times 2 is 4, times 2 is 8, times 3 is 24. So that gives us our prime factorization. And what I like to do, and I'm okay if you leave it like this, but a more condensed form is to say, well, 2 times 2 times 2, well, that's 2 cubed, right? 2 times 2 times 2 times 3. So that could be considered a more condensed form of that prime factorization. So it's not enough to leave it in this state. You need to put them as a multiplication of those numbers. So let's try another one. Let's get this out of the way. What do we got? Sorry, I dropped a paper on the floor here. Let's try 30. And I'm going to do it a little differently this time, just to show you that you don't necessarily have to follow the rules that I had. We have 30. You may notice right away, well, wait a second, I can pull 10 out of that. So that gives me 10. 30 divided by 10 is 3. 3 is a prime number, so we're good over there. 10 is not prime, so now, and I go, oh, wait, 10, that's divisible by 5 because it ends in a 0 or 5. So I pull out a 5, leaving me with 2. Now I have 5, 2, and 3. Those are all prime numbers. So 2 times 3 times 5, the prime factorization of 30. Let's try 72. Okay, so 72. Like I said, I like to pull out 2's if I can, and I see that that's divisible by 2, it ends in 2, so I got 2 leaving me with 36, 2 leaving me with 18, 2 leaving me with 9, 3 leaving me with 3, so I end up with 2 times 2 times 2 times 3 times 3, or 2 cubed times 3 squared. So I did my prime factorization here. Well, here I'm going to show you an example of what this prime factorization can do for us. I want to know the greatest common factor of 30 and 72. The greatest common factor of 30 and 72. Well, how did I do that? Well, I can go through, what we did before was we said, okay, what are all the factors of 30? And we listed them all out. And we said, okay, what are all the factors of 72? And we listed them out. We can do that. But check out what we can do here. We're looking for the greatest common factor of 30 and 72. Well, that means if we're looking at prime factorization, we're looking for the largest number of occurrences of any of the prime numbers that are common between both of them, and that will give us the greatest common factor. So I have 1, 2 here, I have 3 2's here. Well, the greatest common there is 1. There's 1 here and there's 3 here, so best we can do is get one of them. I've got 1 3 here and 2 3's here, so I can get that 3. I've got a 5 here and no 5's here, so I can't get that. 2 times 3 is 6, so 6 is our greatest common factor. Don't believe me? Well, let's try the factors of this. Factors of 30 are 1 and 30, 2 and 15, 3 and 10, 5 and 6. Okay, what about 72? You got 1 and 72, 2 and 36, 3 and 24, 4 and 18, 5 doesn't work, 6 and 12, 7 doesn't work, 8, by the way, 8 is 9, so 8 and 9. So there's all of our factors of that. 1, 72, 2, 36, 3, 24, 4, 18, 6, 12, 8, and 9. So now if I look at these, which ones are common, I see that 1 occurs in both of them, 2 occurs in both of them, 3 occurs in both of them, 4 doesn't occur in this one, 5 doesn't occur in that one, 6 occurs in both of them, 7 doesn't occur in 8 either, 8 doesn't occur in this one, 9 doesn't occur in this one, 10 doesn't occur in that one, 11 doesn't occur in either, 12 doesn't occur in that one. So I'm looking at this and then I get 12, I get up to 15 occurs here but not there, 18's over there but not here, 24 is over there but not here, 30 is over here but not there, 36 is over there, obviously 36 and 72 can't be. So the greatest common factor is 6. So just showing you what we can do with prime numbers and prime factorization we can use that as a way to find greatest common factors, and as you'll see later on, we can also use it as a way to find least common multiples. So there we go, primes, composites, and factors.